Okay, so this is C1.1 packet, our enzymes and metabolism packet, part 2. I was originally going to break them up into the IBSL portion and the IBHL portion. Due to unforeseen events towards the end of the last part, I'm just going to get as far as I can today. We'll see how it goes. Fingers crossed, no tragic ending. And we'll see if we can get through the whole packet today. Alright, so we left off last time at denaturation of enzymes and looking at how their structure changes and how those structural changes specifically at the active site is really what will denature an enzyme. We know that denaturation in proteins in general is just any sort of change in shape to the protein that causes it to lose its function. And so when we're looking at denaturation in enzymes, we're looking at a change in shape specifically to that active site, because that's really what causes it to have its function. That is so severe that that substrate can no longer bind. And so this is the effect of temperature on rate. So this is going to not only deal with when your enzyme is denatured, but also with when your molecules have that high kinetic energy and they're moving around faster, and we can increase our rate. This is like the Y temperature increases rate of reaction for enzymes to a certain point, and then they denature, and then it slows down or stops. Anywhoosies, so when we're looking at these two graphs, this first one here, or this first little paragraph here, is really just trying to get you to realize that there's different temperatures that bacteria can withstand. So different bacteria is going to have different tolerances. Different enzymes are going to have different tolerances for temperature. Same with how it's going to have different tolerances for pH, based on where in the world or where in the body it's supposed to be functioning. So if we look at this graph here, we have optimum temperatures for human enzymes, which peaks at like 35-ish, 38-ish degrees Celsius. And then we have optimum temperature for enzymes of thermophilic or heat-tolerant bacteria near deep sea vents, which is closer to like 78-ish degrees Celsius. And so your enzymes are specific, not only to their substrates, but also to their role. Like, why would you have an enzyme that's not suited to the role it's supposed to be filling? And so you have enzymes that are specially adapted to work at different optimums based on where they are. So we have our human, which has a cooler optimum. Boop, 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 boop. For human enzymes. And then we have our heat-tolerant enzyme with its optimum heat-tolerant bacteria. And the whole point of this little top section, I guess we'll write it in black. It's just enzymes work at temps specific to their role, whether it be in the body or in different places on Earth. Obviously, human enzymes and heat-tolerant bacteria aren't going to be in the same body, hopefully. So it can be location-based, it can be within the same organism. Just depends. And so now we'll look at our graph. This is like a zoomed-in version of one of these. I'm assuming this is some sort of human enzyme because its optimum is about 40, but could be anything. It's like a fake graph, so it doesn't really matter. But so what we're literally looking at is our reaction rate based on temperature and why it has these changes. So let's first look at the first section where we have our increasing rate. We'll make that purple. And so we have our increase in rate up to here. And so to put this slope into words, what we're seeing is as temperature increases, rate of reaction increases, and then the Y, because molecules have more kinetic energy from heat. And so to be specific, that kinetic energy from heat, your enzyme and substrate molecules, or maybe just your substrate, again, some enzymes are immobilized, and so your enzyme and substrate molecules are moving faster. When they move faster, that increases our collision chance, or our chance of collision. Chance of collision between active site and substrate, which equals increased enzyme activity. This is like the explanation-y part of this. And so then we hit our optimum, our peak. Oh, I'm going to make it yellow and then I'm going to regret it. Our optimum temperature. We'll write the yellow part in orange. Optimum or ideal temp is the hottest / most energy without denaturing. It's the fastest reaction rate. And then we start to see a pretty sharp decline, which will make, decline feels like red. Nope, wrong side. Make the decline this like red color. And so that decline is caused because as we start to heat it up, come on. Your enzymes, the actual bonds in the enzyme get too much energy and they start to break apart, causing your enzyme to denature, lose that shape, and the reaction stops, or slows and then stops. So heated above optimum. Chance of bonds in the enzymes breaking increases, which causes denaturing of enzyme, which causes slowing and eventual stopping of reaction. Because once all your enzymes are denatured, they obviously can't do any of that reaction anymore, and so it stops. For your database questions, I would like you to try these on your own. They're good practice. This one I don't think is too hard to see the different lines without the colors, so please try this one on your own. If you have questions, come talk to me, please. On to the next page, where we talk about pretty much the same thing, but with pH. works slightly differently than temperature. Instead of it being about molecule movement, it's really about the denaturing of your enzyme. So again, this top part is just talking to you about how different enzymes have different optimums for what they're used for. So your optimum pH for a digestive enzyme is going to be a lot lower or a lot more acidic than an optimal pH for something that's used in your intestines, just because of the environment that they're in. And so digestive enzymes have their pHs, or their optimum pH, at different ranges, depending on where their activity is the highest. And if you didn't know like what pH was from chemistry, it's just the number of hydrogen ions in solution. Your higher pHs means that you have a higher amount of hydrogen ions, making it more acidic, which means you have a lower pH. If you have a lower amount of hydrogen ions, then you have a higher pH, which makes it more basic. Your pH stays for just percent hydrogen. This is just the percent hydrogen ions, but it's logarithmic, so it's like weirdly flipped. It's confusing. I'm sorry. And so, again, it's low because it needs to work in stomach acid. Low means it's acidic. And this one is like neutral, slightly more basic. Neutral to basic, because in an aqueous or water-based, oh, I should have listed blue. Oh well. Environment. And it goes all the way up to 14, which is more basic. And so explain what happens to the shape of the active site of the enzyme when pH changes outside of the optimal pH. And so key point here is outside of the optimal. What happens to the shape of the active site of the enzyme outside of the optimal pH? And so when pH is outside optimal, let me write part of this in black. Where's the black? When pH is outside optimum, remember, optimum is like that sweet spot where it's going to work at its highest function. Whether it is wrong color, too low, acidic, or too high, basic, the structure of the enzyme, including the active site, is changed or denatured. And enzyme function is decreased. Okay. So now we'll look at the effect of substrate concentration on enzyme activity. I feel like this needs like a heading color. We'll make substrate concentration purple. And so outlining the effect of substrate concentration on enzyme activity by looking at this graph. And so when we're looking at this graph, we can see that with low substrate concentration, we have lower rate. Medium, we get slightly higher. And then high, we kind of level off. So again, your enzymes can only do so much. I think of the little I Love Lucy skit where she's trying to package the stuff and she can't package it faster because she just has too many things. Like she can't work any faster. Her hands are full. And so it's kind of like if you're already writing and you're writing as fast as you can't write any faster. Like you only have one dominant hand to write with unless you're like crazy and ambidextrous. Like the enzymes can only go so fast. And so it gets to a point where increasing that substrate concentration will no longer do anything because all of your enzymes are already busy. They're already all working. And so what I think helps with this picture, because it's kind of hard to tell because it's all gray, is if we kind of color code the enzymes and the substrates a little bit. Make our enzymes green. Oof. I should color these with the thick side so it doesn't rip up my paper. Thick. Here's the enzyme. And then we'll make the substrate. What's going to show up? This one. Oh, it's going to be Christmassy. Cute. It's entirely optional. I just think it makes it easier to look at. And so, oof, sorry, it's hot in here. At your, let me pick a different color for that. We'll do dark blue. At your low enzyme concentration, or I'm sorry, your low substrate concentration, you have a rising rate as it starts to increase the amount of substrate, because your enzymes can then, there's a higher chance of collision with your substrate as we get more, so that increased collision rate. With medium, we have more increased collision because we have more of the substrate, and not all your enzymes are being used yet. You have one that can still be utilized, so your reaction rate will still increase. What's a color that's going to show up? Orange? And then at high, medium. And then at high substrate concentration, we have our maximum function because all of our enzymes are already working, see they're already collided. We have our highest possibility of collision, but it kind of levels off because once they're already all working, that's as high as we can get. We can't ask them to do any more. They're already processing it. They already have the highest rate of collision. Once these ones are done, more will come right in. And that's as high as we can go. And see, they also have very lightly marked out the maximum collision rate. We'll highlight that with blue, I guess. And so once it hits that maximum rate, it's just going to kind of level off. Oh, well, I feel like the boxes should be highlighted too. Oh, I done goofed it. I can't highlight it in blue now. Never mind. The boxes will not be highlighted. All right, so let me get the written out part. So increasing substrate concentration increases reaction rate because chance of successful molecular collision increases. I think that the easiest way to think of this is like, are you more likely to bump into someone in an empty room versus a crowded room? So like, obviously a crowded room. And then your optimum for this would be when all of your active sites are used. Oops, it's tilted, sorry. Once they're all full, can't get any higher. Ooh. So what happens at optimum substrate concentration of an enzyme? What happens at optimum substrate concentration? So at, oh well, it's fine. So at medium to high, concentration, woof, okay, there is enough substrate to saturate or fill the active sites so all enzymes can be working at once, which is your optimum. And so what happens if the concentration increases beyond its optimum point? Increased beyond the optimum. Really nothing. No more combined, so no more substrate off. Substrate can bind to the active site rate will not increase. And seriously, like, if you have never seen the I Love Lucy packing the box clip, it's really great. I will try to link it in the little description. But it's fantastic. It is like exactly this idea. Alrighty. Okay. Oh shoot. I have somewhere I need to be. So we'll cut this short. It'll be another short one. I'll have to film this next part another time. I'm sorry. I did not realize how late it was getting. Whoopsies.